Hi guys, my name is Justin.
Hi everyone, my name's Aksh.
My name's Salman.
My name's Javier.
And I'm Yuvraj. Unfortunately, Angachal was not able to make it with us, but we'll be presenting from the University of Alberta and McCune University. So we're the Oilers team, and our project is basically asking a pretty simple but an increasingly important question is when an AI model reads a patient's clinical notes to flag some type of diagnosis, does it miss real cases more often than not for a particular demographic group compared to another demographic group? And if so, can a common fairness fix called group reweighting actually close that gap? Over the next few minutes, myself and our team will walk you through what exactly we found.
Thanks, UV. So here's the core problem. AI is increasingly embedded in healthcare, but models are still learning from historical data that often reflects unequal access and care. Many studies around the world are showing discrimination present in the healthcare industry as a constant concern, and this new technology could be trained on some forms of that discrimination, which could have massive downside implications. A model can post excellent overall accuracy and still quietly fail certain groups. In this study, we focus on the false negative rate, which is the share of true cases that the model misses because a misdiagnosis can have direct safety consequences. Fairness means catching true cases at consistent rates across groups. So, groups having disproportionate false negative rates mean the technology can learn, train on, and adopt those practices. And this leads on to a research question. Do these clinical AI-based classifiers miss cases unequally across demographic groups? And does group reweighting reduce that gap?
Our method has four stages. First, the data. De-identified mimic 3 discharge summaries, split by ICD-9 codes into 5 binary disease tasks: heart failure, sepsis, AKI, COPD, and diabetes. Second, the model. Bioclinical BERT, fine-tuned per disease. Third, the intervention. A baseline versus a reweighted model that upweights positive cases from a below average prevalence group swept 1 to 5 times. Fourth, we tune the decision threshold to isolate reweighting effect. We evaluate across 5 demographic groups with subgroup false negative rates as our primary outcome. First, baseline performance. On the left, all 5 models showed strong discrimination. AROC from 0.86 to 0.95, but on the right is a problem, the disparity ratio. High subgroup false negative rates over lowest. A fair model sits at 1.0. Instead, all 5 range from 1.43 to 1.93. The headline, strong aggregate accuracy, doesn't guarantee equal performance. The models miss cases unevenly across demographic groups.
So does fairness work? It depends on the disease. This chart shows false negative rate before in navy and after factor 2 reweighting in red. For sepsis, heart failure, and COPD, the missed case rate dropped, diabetes barely moved, and AKI actually got worse. By McNemar test, only two changes were significant, the increase for AKI and the decrease for COPD. The biggest improvement was sepsis, which also had the worst baseline, suggesting reweighting helps most when the model is already missing many cases. Pushing reweighting higher improved recall across all 5 diseases, but with trade-offs we'll see next.
Reducing misses and reducing disparity are different goals. Sepsis improved overall, but got less equitable. AKI got more equitable only because it got worse everywhere else. Heart failure is our clean win. Bottom line, reweighting shifts the operating point. It doesn't make the model smarter, just less precise. Before any retraining, we tried something much simpler, just moving the decision threshold. It matched or beat full re-rating on most conditions, with zero retraining. Threshold tuning should be a standard baseline in fairness work, not an afterthought. Some trade-offs apply though, it's not free.
So, to wrap up, four conclusions. One is that strong overall accuracy does not equal to equity. Every model cleared an OROC of 0.86 and still missed cases unequally. Secondly, reweighting is disease dependent. It helped when its mechanism matched the source of disparity, such as heart failure, but redistributed harm when it didn't, such as acute kidney injury. Thirdly, reducing overall misses and reducing the gap between groups are two distinct goals, and improving one can worsen the other. Lastly, don't skip the simple step. Threshold tuning was often as important and as significant as full reweighting with no retraining. The bottom line is that simple reweighting is not a universal fairness fix, and these interventions need to be validated per disease using a full panel of metrics before they ever reach real patients.